We have stopped last week by the question, how do we produce independent replications of a simulation run? And the key to that is the random number generator. Recording. Now it's done. So a simulation is a program that feeds itself on random numbers to produce some output. So the heart, the engine that we find in all simulators is the random number generator. Of course, there is a trick here, is that simulation programs we do not usually use truly random numbers because it's very complicated to use truly random numbers. Instead, they use pseudo-random numbers that come from a so-called random number generator. The goal of a random number generator is to produce something that could qualify as an IID sequence of uniforms between 0 and 1. So uniform is a distribution of a number where the probability of falling anywhere between 0 and 1 is the same. How can you produce something that appears to be random when it is produced by the computer? Well, to understand why, let's look at a simple example that's easy to understand, and all random number generators are based on similar models with a bit more complexity. The idea is to produce a chaotic sequence. So what is a chaotic sequence? A chaotic sequence is a sequence of numbers that appear to be completely random, even though it is purely deterministic. It is deterministic in the sense that if you give the initial value, which in the context of random numbers is called the seed, if you give the initial value, then the sequence of numbers that is produced will always be the same. So it's completely deterministic. However, it appears to be completely random. So that's one of the key advances in nonlinear system theory, is to have put in evidence this property that some deterministic systems may appear to be completely random, and this is used in a pseudo-random number generator. For example, one that was used in the previous version of the network simulator, the current version is NS3, the previous version was NS2, and it used exactly this one. So the sequence is given by this formula. You compute S, which is a fixed number, the seed, times a to the power n modulo m, and that gives you a number between 0 and m minus 1, and you divide by m. Right? So that was not particularly smart, but that was what was used here. Now, because of this modulo and the exponentiation, when you do things modulo m, some of you have already some experience with that, it's true that it appears to be random. So let's check what it means. Here, I have plotted on the x-axis the values output by a large number of 1,000 calls to this random number generator. And on the y-axis, I plot the quantiles of the uniform distribution. What is the quantiles of the uniform distribution? That's very simple, because the CDF of the uniform distribution is f of x equal to x when x is between 0 and 1. So I'm simply plotting the 10% quantile is equal to 0, 1. So that's very simple. And this is what we can call a uniform QQ plot. Remember last week, we saw the concept of QQ plot, which is useful to test whether something comes from a given distribution. And we typically use it for Gaussian QQ plot, but you can use it for any distribution. Here it's against the uniform. So if the sequence is truly coming from the uniform distribution, it should be a straight line. It is, as we have seen when we spoke of normal QQ plots, it is never really a straight line because there must be some randomness. And here that appears to be the case. So that's a first test we can do, a visual one, but that can be formalized. But visually, we get the idea here of why this appears to be uniform, even though it's completely deterministic, but it's uniformly distributed. Now, this should produce an IID sequence, which means two things. The distribution should be the uniform, but it should be also independent. To test independence, we will see a number of things. One simple test is to test for correlation. All the correlation is weaker than independence. So we will discuss tests in a few more lectures. So if the sequence is truly independent, then the numbers, the autocorrelation numbers, the sample autocorrelation, should be very small, and they should be between the dotted lines, which appear here to be the case. So at least this one passes those two tests. We can do visually more sophisticated tests that are called lag diagram. I'm trying to test whether there is a dependency. For this, I plot on the x-axis xn, and on the y-axis xn plus 100, for example, for this first plot here. I obtain points because I have two coordinates. Now, if the sequence xn is uniform independent, then I'm plotting here a random point whose first and second coordinates are independent and are uniform. Well, if we do this, we are in fact sampling a point uniformly at random in the square here. So if it is true that this random number generator produces an ID uniform sequence, it should appear to be uniform here, which we see at different lags appears to be reasonably valid here. Again, this is not a formal test that we can use, but it gives the idea of what the test will do. Here, we see that there does not appear to be a dependence from xn to xn plus h for various values of h. Right. So xn appears to be independent of xn plus h. This is what we call a chaotic sequence. However, of course, everything we do here is a bit cheating, so we need to be careful about one thing in particular, that's the period. This random number generator appears to produce an ID and uniform output, but in fact it is a sequence. Now, this sequence is in a finite state space. Since the sequence is purely deterministic, once we reach the same value, we will reproduce exactly the same sample. In other words, it is periodic. So any sequence generated from a deterministic algorithm in a given computer must be periodic here. Now, for the NS2 simulator, the period is 2 billions, which is large for individual things, but when we do simulation in the computer, which is too small here. So if the random number generator is periodic, of course, that's embarrassing. That means that if you do long simulation runs, sooner or later, you will do the same thing again, which is the opposite of randomness. It simply means that the tests we did a few seconds ago are not looking far enough into the time diagram to be conclusive. So of course, this NS2 simulator is not used anymore. Its period is way too small. And modern random number generators, for example, MATLAB's default is the Mersenne twister, which has a period of that size. So it does have a period, but the period is an astronomically large number. So the expectation is that this does not matter because it is so large. What can happen when the period is too small? Well, here I did a simulation of the very similar to what we discussed a few lectures ago of the throughput of mobiles when they're using TCP. When I used a random number generator to produce random numbers. Why did I use random numbers? Well, I was using Wi-Fi, and in Wi-Fi, there is exponential backoff that whenever there's a collision or you don't receive the acknowledgement for a packet, you draw a random number to know how much time you wait until trying again. So it is in the essence, in the nature of the system I am simulating, where I needed random numbers, but also I wanted to simulate the mobility of systems. So instead of simulating based on detailed traces, I did what we often do. I used a mobility model that also has some randomness here. So that's a compact way of simulating the complexity of the real world here. And I used two random number generators, this old style number generator and a more modern one. And I computed confidence interval for the throughput at different points in time here. Of course, I obtain different samples because the output is random. And if I use a different random generator, I have no expectation that I would obtain the same output, hopefully. But I computed the confidence intervals based on independent replications, and I see that they are very different here with the two random number generators. In fact, what has happened is that this random number generator has some residual correlation, in that case, that is probably negative, that introduces some bias in the protocol itself and in the the replications that are not truly independent. So those confidence intervals are not correct here. The true things is much better than what we thought. In fact, we can put the finger on what happened when I do two streams. So two streams is the thing I will naturally do when I do a complicated simulation on a multi-threaded in a multi-threaded environment, like we very often do, because the way to take advantage of the power of modern processors is to have multi-threaded programs that can run in parallel as long as they don't compete on similar resources. So if you do a complex simulation, you may need to compute the evolution of a state at one point. And if you know this evolution can be done in isolation and does not affect another computation, then you would start the other computation and do it in parallel. Here I'm showing what happens when I start two streams of the random number generator, the NS2 random number generator, with two seeds. When you write your program, you will have to give the value of the seed. If you don't give the value, it's the default environment will choose it for you. And for example, if you run MATLAB, if you start your MATLAB process from scratch and you do it 2 times by restarting for the second time, then the second execution with the same will produce the same string and will produce exactly the same thing. That's the deterministic part of this random number generator, which is good or bad. It's bad because we would like things to be random and they are not, but it's very good for debugging, because that means while we're debugging the program, if we give the same seed, we can see what is expected, and we can check whether our bug fixing is correct or not, which is more difficult when the output is truly random. Here I had 2 parallel threads for execution, and I had to give the value of the seed. So of course I will not reboot my MATLAB session. So what I need to do is to explicitly give the value. I need to get it from somewhere. So I did what everybody does. I gave 1 for the first and 2 for the second. And now I'm plotting the value of the output of the random number generator of the first stream versus the second. And this is what we see here. So I have here a random number. Here I have another random number. My 2 threads are supposed to simulate independent things. So those 2 numbers should be independent. Is that an example of 2 independent coordinates? Then of course not. 2 independent should look like this. It should give me something uniform in the square. Here they're not at all uniform. If the value of the first is 0, 2, the value of the second is completely determined by the value of the first. It is, so there is a very strong dependence, in fact, and this is due to the fact that I'm using the same random number generator with different seeds, and there is usually a strong correlation between the 2. So first thing to watch, when I have a random number generator and I use it for independent replications, I cannot simply give deterministic seeds that I compute out of my head. I need to be more careful. There's 2 ways to do it. The first one, which is expensive, is to draw the seed by using a true random number. There are ways to do that. You can imagine a program like moving my pointer on the screen. You could use my random movement on the pointer to generate a random number. There are programs that do that. So based on inputs by the user, and a program that will analyze this input to provide a truly independent seed. There are websites that do it. Or you can use random number generators that have thought of this problem and support parallel streams. For example, if you use this stream, which is a special stream in MATLAB, not the one that comes by default, that's a stream that's able to produce independent streams for you, so that presumably it will compute a random number using itself in a way such that the dependency that I gave before will not exist here. So that's something to watch when you do simulations. You need to be careful about how you use the random number generators here. Voila. So once we have a computer and a program that is able to produce random number generators, random numbers between 0 and 1, all the rest follows from that. So the randomness is entirely encapsulated in this basic function that produces the random numbers. So now we have practical problems, like for example, if I give you a distribution f, one-dimensional, but we will see also multi-dimensional, how can I compute a program that will give me a sample from this distribution? So most of the time, this is packaged. For example, if I want to give a sequence of n random numbers that come from the normal distribution, MATLAB will do it for us. So in that case, we will use the MATLAB function rand n and the variance of it. And there are similar functions that are more or less copied from MATLAB in NumPy, for example. But it doesn't do it always, and there are many instances where we need to do it ourselves. Therefore, we need to learn about the two classical methods for that are called CDF inversion and rejection sampling. So with that, you're equipped to produce practically all distributions. So the first one, CDF inversion, is for a unidimensional random variable. So I have a distribution that produces a number and has a CDF capital F. So knowing capital F gives me all information about the distribution. Then I have this following property that says that if I draw a uniform number between 0 and 1, here, between 0 and 1, and I take the inverse of the CDF applied to this random number, I will obtain something that is in the same space as my random variable, and it will have a distribution that has exactly the CDF that is this function here. Observe that my random number u is between 0 and 1, which makes sense because the CDF, remember that capital F of C is the probability that my random variable is less than C. So the probability P, we're in this P space, is between 0 and 1. So that makes sense based from the numbers viewpoint. Quick idea of the proof to reveal the magic that's behind that. Well, the property that we're using is that a uniform random number has a value less than 1 when u is between 0 and 1 is exactly equal to u. Right? So the CDF of the uniform distribution is the identity function for u or p between 0 and 1 here. That's so the probability that uniform is less than 0.6 is exactly 0.6. So if I assume for a second to simplify the story that f is a continuous increasing function, then f can be inverted. Now, if I compute f minus 1 of u, where u is this uniform here, I will have the statement saying that for a fixed little x, saying that this random output is less than little x, is the same as saying that by applying f, because f is monotonic increasing. Therefore, saying that the probability that this event occurs is equal to the probability of this event. Now, I apply this here. F of x is u. The probability that u is less than f of x is equal to f of x, right? Which is this property here. P that u is less than little u is equal to little u. So here my little u is f of x. So we see that the CDF of the random variable capital X is precisely my function f. At least in this simple case, this is the proof. So you see, it's very basic, but that's very powerful. For example, a variable that we will very often use is the exponential random variable. The CDF is 1 minus exponential minus lambda x. So that can easily be inverted. How can I find the inverse of that? Well, I solve for f of x equal p. So that's the equation I have to solve and obtain the solution. X is minus log, ln here is the log, 1 minus p over lambda here. So I can now replace, take as argument of this random variable u that's uniform between 0 and 1. So if I do a program that computes minus log of 1 minus u divided by lambda, that's my capital X, and this will give me exactly an output that has the exponential distribution with parameter lambda. Now, because u and 1 minus u have the same distribution, if u is uniform between 0 and 1, then 1 minus u is also uniform. Uniform means all values take the same role, so 1 minus u will give the same thing here. Therefore, here is a simple formula to give a sample of the exponential random variable minus log u over lambda here. which is also an interesting way of thinking about the exponential distribution. We see in particular how the parameter lambda plays a role into the exponential distribution. So we can think of a distribution through f, its distribution function, or through a formula to simulate it from a uniform. That's two equivalent ways of thinking of a distribution. And this one tells us that if I change lambda here, if I double lambda, it's the same thing as divided x by 2. Of course, this is a formula between random numbers. Whenever I give you a random u between 0 and 1, I compute x in this way, and I obtain a random x that follows the exponential distribution with parameter lambda. The exponential distribution, we'll come back to it. That's one that's very useful for modeling noises. This is also why, because the formula is so simple, this is why MATLAB, for example, doesn't give you a formula for producing a sample from the exponential distribution, because they expect you're able to do it yourself. What I explain here is when the CDF is continuous and strictly monotonic, so increasing. Sometimes, very often, in fact, when we have discrete variables, the CDF has jumps here. Here, this is, for example, showing a function that takes some values on the x-axis. Whenever the CDF hits those values, there's a jump here because the probability of being less than the value also has a sudden jump here. So the formula here is the same, except we should not take the inverse, which does not exist, but what is called one of the pseudo-inverses given by this formula here. What does this formula mean? Well, it means that if I give you a value p on the y-axis, I compute for the largest value on the x-axis such that f of x is less than p. So I draw p here. So the values of x that are less than p, that gives me all this interval. So the inverse is this value here. You see, the pseudo-inverse gives me this value. And the theorem plays, it's a bit more complicated to show, but it applies here. So that's another way to provide samples from a distribution that has jumps. So for example, if I have a random variable that is integer, for which I know the probability of a value k for every k, I need to compute the cumulative probabilities, which are the CDF in some sense. By convention, f minus 1 is 0. Then I compute the f minus 1 of p is obtained by solving this problem. Find the largest integer n such that fn is larger than or p. Now, if fn is sorted, then this is searching through a sorted array, which has a logarithm complexity. So the problem becomes, draw u using the random number generator and found an output n that satisfies this, and you can convince yourself easily that this is equivalent to looking for the integer n that satisfies this constraint here. The integer n is then your random output here. For example, if an integer takes uniform values between 0 and 9, I'll say uniform, but this is integer uniform, which is not the same as the uniform I said before. So the values are 0, 1, 0, 2, etc. So I draw u using the random number generator. If u is 0, 22, for example, well, the largest value of n, such that n is between the two, gives me 3 here. If u is 0, 78, n is 8, for example. The Poisson distribution is given by this formula here, so I can similarly have something a bit more complicated that can be computed numerically, but we will see that there are smarter ways to find samples from the Poisson distribution. A distribution that is also useful to think theoretically is the geometric distribution. There are variants of the geometric distribution depending on we consider that it starts at 0 or at 1. Here it's the version that starts at 0. So geometric distribution is the number of successes or the number of failures in a sequence of binary outputs. So I try at random successively, and I draw a number which is 0 or 1. With probability theta, I obtain a 1 here. and I ask the question here. What question do I ask? What is the first time that I obtain a 1 here? And my first time, the first index is 0 here. That will give me this formula here. So if you imagine at every nanosecond you shoot with a photon, for example, and with very small probability, theta, the photon will arrive here. If it arrives in the first slot, you say that my output is 0, and you repeat that time after time. So if you do this, you have the arrival or not of a photon, and this arrival will occur for the first time at time k with this probability here. And this has the property that the decision whether a photon arrives in a given time slot, this decision is independent of what has happened in all the previous time slots. So this is what we use when we want to model an arrival of events where the arrival is completely independent and from the past and memoryless. Whether something occurred just a few microseconds ago does not give you any indication whether it will happen again. Right? This is what we call a memoryless arrival process in discrete time. In discrete time, then it's very easy to think about it. It is given by this flipping a coin at every time slot and decide whether something will come. Why I say all of this about this distribution, why is it interesting? Well, because it's a distribution that helps us to think about the exponential distribution. The exponential distribution has the same property. If we consider that the arrival of events are exponentially distributed, then given that this event has not yet arrived, I have no information on whether it will arrive very soon or I need to wait for much longer time. So if you think about it as a lifetime, having observed that some system has lived a certain duration gives you no information on when it will die or not. So that's memoryless, and that's a property that we will need to detect here. So that's a very easy way to approximate. The exponential distribution is a bit complicated to handle because time is continuous. The geometric is easier to, at least to reason about. Now, how do I sample an output from the geometric distribution? Well, I apply the formula that I said before. With the constraint, I have to invert P. So given P, I need to find a number n that satisfies the two constraints we had before. It's between Fn and Fn minus 1 and Fn, which gives me this constraint here. And we can see that this is very simple. Finding an integer such that this integer brackets and the next bracket is given quantity is simply the floor of this quantity here. So this is how I will obtain a sample. I take the log of 1 minus p divided by log 1 minus theta. Now I replace p by a uniform from a sample from the uniform distribution. Same trick as before. 1 minus u has the same distribution. So to obtain a sample from this, I can do simply logarithm of the random number generator output divided by logarithm 1 minus theta, and I take the floor of it. If you compare to the exponential distribution we saw, we take this value, minus logarithm of u divided by lambda, then we see that the geometric distribution is exactly an approximation. It's in fact a quantization of the exponential distribution, where we replaced lambda by minus log 1 minus theta here. So we can map the lambda to minus log 1 minus theta, and if theta is very, very small, this is approximately the same as theta. Voila, that's how we can use the CDF inversion formula to compute, to sample from a distribution. For example, here's a little quiz for you to think. I have written a program that does the following, or a function. I call rand. Rand means my random number generator. I have an output which is between 0 and 1. If it's less than p, I return 0. Otherwise, I return 1. What is this thing providing? I close the poll in a second. And the majority says B, which is, of course, the correct answer. Well, if you think about it, the random, this is my value U. Think P is equal to 0, 2. What is the probability that U is between 0 and 0, 2? Well, it is exactly 0, 2. So if this algorithm will produce 0 with probability P and 1 with probability the rest, 1 minus P here. So the answer is B here. So here is how we can simulate very simply the flip of a coin. Of course, we need to make sure we don't do mistakes in the boundaries. We don't flip A and B. We will very often have to simulate things that are not just one-dimensional. And the simplest case that is not dimensional is in dimension 2. Very often we'll have much, much larger dimensions, but that's difficult to visualize. Here is a quick question. Here I have two samples of 10,000 points in the square 0, 1, 0, 1. It doesn't look like a square because the y-axis is a bit compressed, but this is the square. Which one is 10,000 samples of the uniform random number generator? I close the poll. Where is my window here? The majority says B, which is the correct answer. In fact, A is suspicious. A is regular. So what I did in A, I draw regular lines here with equal spacing. So it's non-random. The points are very deterministic. And B was truly a sample from the uniform distribution. So the answer is B. By the way, how do you sample a random uniform point in a rectangle? Let's say the rectangle is the square 0, 1, square 0, 1. Do you want to share, to annotate my screen and try your answer? So one proposal is using two independent uniforms to pick X and Y exactly, which means you can do simply, that would be a program that produces a point XY that is exactly. Now let's go to a slightly more sophisticated question. If my rectangle is not 0, 1, but something else, then I can do a simple rescaling. That's an observation I did, if you remember. I said U and 1 minus U have the same distribution. Well, if I rescale by a fixed quantity, then I may change the distribution, but if I do a linear change, I will transform the density by a constant. So if I draw two numbers uniform between 0 and 1, in order to make them fit the rectangle, I have these simple affine formulas here that will produce numbers that are uniform in a certain rectangle. It's one way to do it. Right. So we'll use that a bit later. So now let's come to the real reason for that. Assume now I want to draw a point uniformly in this area. This area is the Swiss cross, so the Swiss flag. I want to draw a point uniformly in this area here, which I did here. Right. So first question, if I do this, I draw XY uniformly in this area, does that mean that X and Y are independent? I close the poll in a second. The majority says no. And the answer is, well, in reality, it depends. We have seen that in the specific case of a rectangle, the answer is yes, at least for a square, and for a rectangle, it's the same. For a general area, the answer might be more complicated. For this specific case, the answer is no. How do we see that? Well, independent means, remember, it means whether the distribution of y given x depends on x or not. How do I get this distribution? Well, a poor man's way of getting it, based on simulation, is to look at my points here. I plot, for example, x equal x minus 5. I have obtained, and I look at all the points that are on the same line. Of course, they are not exactly on the same line, so in practice, I will do a little bar around it, and I look at the points that are here. So those points that are on this green bar are samples of the conditional distribution of y, given that x is equal to minus 5. I can do the same when x is equal to plus 5. I will have this other bar here. What can be seen is that with a bit more work, we can compute the conditional distribution. We'll see, but what is obvious here is that the bounds are different. Given x is minus 5, we know that y is between 0 and 20. Given that x is equal to 5, we know that capital Y is between minus 20 and 40. And in fact, they are uniform on those two intervals. So the distributions are not the same. They depend on x, which is one way we have seen of expressing that two random variables are not independent here. So they are not independent in this specific case. So let's move on a bit and try to understand what is the uniform distribution in an arbitrary area. Here, this area, which is not so complicated, but has enough complexity to show the general problem. What is the PDF of the distribution of a random point in this area here? The PDF, the random point, I know the coordinates by xy, so it's a PDF in 2 dimensions. So here are 2 possible values, and perhaps none of them is correct. So what do you think? I close the poll. The majority says something else, which is a very wise answer, just in case, and is the correct answer here. Well, first, the definition of the uniform distribution means constant. So uniform, a random variable in a Euclidean space, is uniform on some subspace, at least for spaces that are like A, have a non-empty interior. That means that the PDF is a constant here. Now, what the value of the constant is, well, in fact, it cannot be 1. That was, so the first answer was almost correct, but the constant must be such that the total probability is 1. So the true answer is this one. The PDF of xy is 1 divided by the normalizing constant when xy is in A and 0 otherwise here. What is the normalizing constant? Well, the normalizing constant is such that the integral of the density over A is equal to 1. So the integral of 1 is the area, so that means that the normalizing constant is 1 over the area. So that's one way it's one way of defining the uniform distribution, or says the standard way of defining the uniform distribution of an area such as A here. The next question is how to sample a point uniformly in this area. Here I'm proposing two algorithms. Algorithm A does the following. I draw a uniform between -10 and 20. -10, 20 is the x-axis. And I do a switch. If the outcome of this is between 0 and 10, which is that here, I draw a uniform between -20 and 40. Else, presumably it is in one of the two other border areas, I draw a uniform between 0 and 20. That's algorithm A. Algorithm B follows a different rule of thought. It says, I draw X uniform between -20, 10, and 20, and Y independent. So we know that if we do two calls to the random number generator, they're independent. So X and Y are independent between -20 and 40, which means I draw a point in the bounding box here, uniform in the bounding box. And I do that until it falls in the air into the area of interest. So if the point is here, for example, then bad luck, I do it again. If the point is here, I keep the point. Those are my two algorithms. Do you think that any of the two is a correct implementation of our simulation? I close the poll in a few seconds. And the majority says A, which is incorrect. The correct answer is B. But this is perhaps surprising. And the reason we see this very simplistic example is because of the intuition it gives about what happens in reality. So we have two things to understand: is why is A wrong, and second, why is B correct? Those two things are interesting per se. So why is A wrong? Well, if I draw X at random between -10 and 20, I do that uniformly. And I keep X. So X should be the first coordinate of my point. Perhaps you remember from your probability course the concept of a marginal distribution. The marginal distribution is a distribution of X when we draw XY. So if I take one of those red points at random among the points that are here on the map here, this is one way of thinking of a distribution, which is a bit contorted, but is very helpful. I first generate 10,000 points of this distribution. I put them on the map, and then I randomly pick one of the 10,000. That gives me an approximation of my distribution. It's a very powerful technique. It's called Monte Carlo sampling, or we'll talk also about the bootstrap. So we can reason in this way. So you take all those points here, and you take all of them, and you look at only their X coordinates. And then you put a point on the X-axis only. If you do this, well, what will you see? Well, you will have more points here between 0 and 10 because they're uniform everywhere. So there is, roughly speaking, 3 times more points between 0 and 10 than in the other two parts here. So the PDF, the distribution of the marginal distribution, the distribution of X, should have a higher probability of being between 0 and 10. In fact, the probability here should be 3 times larger than the probability of being here or of being here, which will not occur with this thing here. So the correct X is not uniformly distributed on the X-axis. It has a higher chance of falling between 0 and 10. And we can see that this ratio is 3, because if we count the number of points here, roughly speaking, there are 3 times more points because the area is 3 times bigger. So that's why A is incorrect. And that's also an invitation to think carefully about independence, uniformity of marginal distributions. And also one technique to think about it is to reason about distributions, to imagine we do exactly what we did here. We do a simulation of a large number of points and we simply count. Now for B, why does it work? That's a bit more tricky, but we'll see that in detail. So what B does is first compute a point uniformly at random in the bounding box here, and do that until the resulting point is in area A. Right? So this has a name, it's called rejection sampling. So we draw a point xy from a certain distribution, which is not the distribution of interest, until it passes a certain test. Then we will see in a second that whenever you do that, the outcome of your program is a sample of the conditional distribution of xy given the condition xy belonging to A. We'll see that in theory in a few more seconds, but here we can do manually the proof. We can compute the distribution of what we do. I draw xy uniformly at random in the bounding box, and I want to compute what is the probability of xy given that xy is in A. So that's a conditional probability. How do we compute the conditional probability? The theoretical way is a bit more sophisticated than what I say here. I'm just giving a physics-style formula, assuming things can be discretized. I want to compute to compute the PDF, for example, I want to compute what is the probability that xy is in this box of length dx dy, conditional to the event here. Right? That's the probability I want to compute. Now, where I do the physics-style trick is I will pretend here that dx is so small that those things are as if they would be discrete. It's a unique choice here. So if this would be discrete, a conditional probability is something complicated when variables are not discrete. When they are discrete, it's very simple. So let's assume they are discrete here, or let's pretend they would be discrete. Remember that the conditional probability is the probability of the and divided by the probability of the thing that we condition upon. So it's the probability of this and that divided by the probability of that. So the probability of this and that is the probability that we fall. So I will draw exactly what it means. It means I am taking here a little box somewhere here. So this is my x, this is my y. And I take a little box here of length dx dy. And what's the probability of the joint event? I am in this box and the point xy is in A. Now, if the box is very small, well, since little x, little y are deterministic quantities, this is something non-random. If I pick xy in the area A, then the box is entirely in the area. If the box is small enough, and if xy is not just on the boundary, otherwise it's entirely outside. So that means I have a binary thing here. If the point is in A, this indicator means it's 1 if the condition is true. So this is 1 or 0. And if the point is in A, the probability of this here, the and, I replace capital X by little x because they're quasi the same when dx dy are close to 0. And the and is taken care by this. And then there remains the dx dy. The probability of falling in exactly this box here is proportional to dx dy. So that will give me this. And the denominator is the probability that if I pick a point at random in the bounding box, I fall in A. Well, this should be proportional to the area of A here. So that tells me that at the end, with this heuristic argument, the PDF that I obtain is a constant divided by the area times the when we are in the area, which, if you remember, is one of the definitions of the uniform distribution. So this is why B produces the correct sample. In fact, B is an instance of a generic method called rejection sampling, which I'm presenting here in all generality. So the framework is as follows. Assume I am able to produce two random variables, x and y tilde here. Then I do the following. I'm able to produce two random variables, x tilde and y tilde, according to some method. Very often there will be samples of the uniform distribution because this is what the random number generator gives to us, but it will not always be the case. So I do the following algorithm. I draw x tilde and y tilde. Again, x tilde and y tilde are not necessarily independent. In this case, it's very generic. It's just a joint thing. I have a method, a simulator, that can produce an output of x tilde, y tilde. And assume I do this until I'm satisfied the criterion that the second coordinate, y tilde, satisfies some constraint. The constraint I express it in this form, y tilde happens to be in a subspace A here. So I do that until that happens, and then I return x tilde. When I do this, I have a sample, x tilde, of the distribution that is equal to the conditional distribution of x tilde given y tilde is in A. Right. So that's a very important fact. It seems obvious, but many things seems obvious in terms of distribution, and we've seen in the previous quiz that some things that may appear to be obvious are sometimes not true. So here it is obvious and it is true. So if I draw jointly x and y tilde until I'm happy with what y tilde did, I obtain something that has the the conditional distribution of x tilde given y tilde satisfied the criteria. For example, what we did a minute ago to obtain a sample of the uniform distribution in this area A, we drew a point uniformly in the rectangle until it was in A. So here, what did we do? Well, we drew x tilde, which was the point xy, until the criterion on y tilde, here y tilde was exactly the same as x tilde, right? So until the y was belonging to A. And what we obtained was a sample of xy, given that xy is in A, which is the uniform distribution in A. So another way to look at it, I computed a point, the red point, uniform in the bounding box. I rejected it whenever it was not satisfying the condition. And what I return here is, of course, a point that was red at the beginning. But the key thing, and that's what probability are about, the key thing is that the distribution of what we have at the end of our filtering, of the selection here, is not the same as the initial distribution. In fact, that's visually here very clear. What I have here for the original distribution is uniform in the bounding box. What I have at the end is uniform in area A. So that is what rejection sampling will provide. Remember this fact, when we do rejection sampling, the distribution we obtain at the output is not the distribution that we sample from. For example, if we would like to sample uniformly a point in the unit disk, here I'm plotting the unit disk here. The intention here is just to color the disk, not to present samples here. Then I can use rejection sampling with a bounding box around the disk. It's not the best method to draw a point uniformly in the disk. We might see a bit later there are smarter methods, but here that's not the purpose. We can pick a bounding box, for example, the smallest one, that is the smallest square, that would be this one here. I draw a point uniformly, and then I do the test. The test would be, is x squared plus y squared larger than 1? If this disk is centered on 0 and has radius 1, I do that until the condition is, until the rejection condition is false, and then I will obtain a point that's uniformly distributed in the disk. That's one way to do it. Another way is to do the same with a larger bounding box. The theorem says it will work the same way. The difference will be the number of iterations. Of course, if I have a larger bounding box, I will fail more often. Therefore, the number of iteration will be larger in case B. So this will be less efficient because the code will run longer, and the largest part of the computational cost in this exercise is to do a call to the random number generator, which is way more compute intensive than all the tests we did here. So there is some freedom when we use rejection sampling. We don't need necessarily to have the optimal bounding random variable. Anything that is good enough might be used at the expense of optimality here. So let's see if that can be used for profit here. I'm submitting to your sagacity the following pseudocode. I sample a random number uniformly between -10 and 10. I compute q equal f of x, where f is this function here. That's the sinc cardinal sign, which is very often used in signal processing, right? So I compute this weird thing here, and with the probability equal to that, I return x. Otherwise, with probability 1 minus q, I do it again. So it's not exactly in the form I gave before. What is this algorithm computing? I close the poll now. So this is a bit more of a mysterious thing. The correct answer is A. Well, intuitively, the algorithm is choosing a point between -10 and 10 with a probability that's proportional to the PDF here. So at least as a hand-waving argument, perhaps it would mean that it draws from the PDF-F. But admittedly, this we need to be careful. So we will see the proof next. In fact, this is an application of importance of rejection sampling. The first thing to observe is that in this method, the normalizing constant, in this case, is given by this formula here, which is the integral of the PDF I gave here. The interesting thing is that with this method, we don't need to know the constant to sample from the distribution. So this example is an immediate application of rejection sampling. That is one of the practical uses of rejection sampling, which can allow us to draw a sample from a distribution that is known up to a normalizing constant. If we know the normalizing constant, it doesn't hurt, but if we don't know it, it doesn't matter. So I call Fy superscript n is for the non-normalized constant. So we have a function and we want to draw from a distribution, so this function has to be non-negative, such that the PDF would be proportional to the function here. And for this, I assume that I have another distribution from which I can sample. For example, in the case we had before, uniform between -10 and 10. So assume I know how to draw a sample from a random variable x. Also, I must know an upper bound on the ratio of the function of interest and the PDF of the function from which I can sample from. In particular, this PDF should be positive, should not be 0 here. So I must know an upper bound here. And then I do the following. I draw from X, and then with a probability that's given by drawing from U, I draw U uniformly between 0 and C. If U is less than the ratio of the distribution of interest and the distribution of the machine that I used for F, I accept. If it's above, I reject here. And if I do that, I will exactly obtain a sample from the distribution that's proportional to this thing here. This is exactly what we did in the previous quiz. I wanted to draw a sample from this cardinal sign function here, squared function here, condition restricted to a finite interval. This is positive. This has a mass over the entire real numbers, but here I bound it between a, minus a and a. Then if I want to draw a sample from this, I do exactly the algorithm that we saw before. I draw a uniform between minus a and a. So my distribution for the uniform is this. Remember, the uniform distribution is constant with normalizing constant equal to the total mass. I said the area here, if it's a one-dimensional variable, it's the length of the interval, so it's 1 over 2a. So this is my fx. I have to compare the ratio f, the non-normalized density divided by fx. I do the maths, and I found that this is, so I forget about the normalizing constant. You know, perhaps that the cardinal sign is less than 1, so an upper bound is 1. In fact, we see it on the graph here. So an upper bound is 2a, so I take c equal to a, and that gives me this algorithm. Draw x uniformly between minus a, and u uniform between 0 and 2a, and if u less than this, return capital X here, right? Which is almost what I did, which is almost what I did in the algorithm there. I can rescale things a bit. Instead of doing this, instead of drawing u uniform between 0 and 2a, if I draw it uniform between 0 and 1, then the relation between u and v are this one. V is equal to u divided by 2a, so the test is changed here, and that gives exactly the algorithm we had. If v is less than the normalizing density, the non-normalized density, we keep it, otherwise we return it. So the interpretation is, I draw here a number, in this case uniform, between 0 and 10, and I draw another number which is between 0 and 1 here. And if I am below, I keep it. If I am outside, I reject. And this will give, if I do that a zillion times, I will find a histogram which will be proportional to the, which will be an approximation of this curve here, because if I do it 1 zillion times, for example, the number of times I will succeed at position x will be exactly proportional to f of x. That's perhaps an intuitive explanation. You have the proof in all details in the lecture notes here. So to obtain a sample from a distribution that has an arbitrary density, we have a generic method, not necessarily the best one, but that's a backup solution that always works. If the density has a bounded support between A and B, I can draw a uniform between A and B. If I need a safe upper bound on the ratio between the non-normalized density and an upper bound on the normalized density, and that gives me this algorithm here. So I draw a random number between A and B, U between 0 and M, where M is an upper bound on this normalized, non-normalized density, and I do that until I return my test succeeds here, as we have seen in this example. So I did something similar here. Now this is very interesting, in particular when the CDF inversion formula doesn't work for whatever reason, in particular if we have a dimension more than 1 for the random variable. So here, so in order to get a feeling for things, let me start with a first intuition setting drawing. Here, I have three distributions that are known up to a normalizing constant in the box 0, 1, cross 0, 1. So the square, the unit square here from 0 to 1. And I have three distributions that are known up to some normalizing constant. And I did three simulators to generate a point image. Which one is drawn from which simulator? Can you place the boxes correctly? I'll close the poll in a second. So the majority says CBA. Well, certainly one thing that is clear is that B, so is the uniform distribution. It's a normalizing constant, which is 1 in this case, but I wanted to force your intuition here. So B is the uniform distribution. This is correct here. C, so the majority says C, the majority is usually right. So C should be the first one. So what does the first one say? The first one says that the PDF is equal to the distance to 0,505, which is the center here. So if the PDF is the distance, that means it's very small here and much larger there, which is what we see here. We do see that it's darker the further we go from this, so that's reasonable, that's C here. A, well, we can interpret A as the distance from the point to this line here. That's the second counter diagonal here, the second diagonal of my box here. And we see indeed that if the points are on the line, the density is 0. If they are close, the density is small, so we see fewer points. So that is correct. So that's one way to visualize densities. And I see that your intuition works well. Okay, now how would you do this exercise? How would you draw a sample from this distribution here with a PDF proportional to that? Which algorithm is a correct sampling? I close the poll in a second. And there's a tie between both and A, and the correct answer is both. In fact, both are correct implementations. They use different upper bounds. One is certainly a safe upper bound for the distance from a point in the unit square to the center of the square, but 1 over square root of 2 is a better bound, but both will work. The difference is that the first algorithm will be more efficient in terms of number of iterations it will use. So both will work. Very often, of course, in a case like this, you would use implementation A. There's no point using B when it is so simple. Sometimes computing a bound is very complicated. If it's very complicated, then you simply don't do it, or not in the first phase before optimizing your problem. For example, if I look at this program here, I obtain a PDF proportional to the absolute value of the difference, which is very similar to what we saw a minute ago. So take-home message, with this method, you simulate pretty much anything you want, at least as long as you can compare it to one distribution, which is certainly true when there is a compact bounded support, also in some other cases. There are also, so we have seen two standard methods, rejection sampling and CDF inversion. Those are really the two methods of choice that you must know because you will need them very often. There are other methods that have been optimized for specific cases. For example, the very frequent case of the normal distribution. Well, we could use the inversion method, but there is no closed form for the inverse of the CDF. So the CDF can be computed numerically, but it's also expensive to compute it numerically. So it's a bit complicated. Rejection method is also possible, for example, by comparing it to an exponential distribution. But in that case, there is an ad hoc method, which says that if we want to draw not one normal random variable, but two independent, then it's cheaper. That's a paradox. Sometimes it's cheaper to expand the dimension of what we're doing, because if I draw at random two Gaussians, I obtain a point that has circular symmetry, and we know the distribution in polar coordinate. The angle is uniform between 0 and 2 pi, and the radius has another distribution that can be computed by applying the formulas for changes of distribution, to which we can apply CDF inversion. So we can compute the radius of this point with CDF inversion, and the angle, it's uniform, so that's easy to compute. So we can obtain 2 points. So if you ask MATLAB to obtain 1 point, MATLAB will in fact compute 2 and throw away the second one. If you ask MATLAB to compute for you 200 points, then MATLAB will draw 200 random Gaussian variables. MATLAB will draw 100 two-dimensional Gaussian vectors here. This is, for example, a sample of 100 points from exactly what I said, the Gaussian vector xy with 0 mean and covariance matrix 1001, which in the specific case of Gaussian, this is exactly saying the same as x and y are Gaussian distributed and are independent. Independence here is because the covariance, the cross covariance terms are 0 here. For Gaussian vectors, non-correlation is the same as in R as independence. Otherwise, as you will see in the quiz, in the exercise to be done after this course, you will see it's not the case here. For example, here is another example of a Gaussian vector that has this covariance matrix. So the variance is 1 for x, the variance is 1 for y. The terms of the covariance matrix are here the variance on the diagonal. The non-diagonal terms are the covariance. We see the covariance of x and y is non-zero, which is a symptom of it being non-independent. And we see also this independence can easily be seen. Non-independence here is, for example, the fact that if x has a value that is here -2, we see that the distribution is y will tend to be here, whereas if x has a value +2, the distribution of y will tend to be here. By the way, what is the distribution of y on this example here? I close the poll in a second. And the answer is A, normal with mean 0 and variance 1. If you're not familiar with Gaussian random vector, I think it's time to have a look at the appendix of the lecture notes, and many of you are, but if you're not, you should have a look at the appendix of the lecture notes. So there is everything you need to know about Gaussian random vector. So a Gaussian random vector is, for example, Ix is a multi-dimensional distribution such that any linear combination of the coordinates will give a Gaussian random variable. That's one way to define it. And in particular, if I take as linear combination of x and y 0x plus 1y, that gives y. So the marginal distributions are random, are Gaussian distributions, and the covariance matrix gives us the variance of the distributions here. So the variance of y is 1 because the covariance matrix is 1. The fact here that the non-diagonal terms are non-zero means this is a Gaussian random vector where the coordinates are not independent. And those of you who heard about principal component analysis, for example, will realize that this is used to capture the dependency of random variables in data analysis. Voilà. So we have spoken of how to sample from a distribution, which is a common exercise we have in simulation. We have this need because we want to simulate our system, and most of the time, very often, we have a random component part in our simulator. But there's also an interest per se in numerical analysis. When we have complicated quantities to compute, sometimes simulation is also a good way to do it, at least when this has to do, this can be formulated as an expectation. So the topic now is Monte Carlo simulation, the simplest Monte Carlo simulation. There's also Markov chain Monte Carlo simulation, which is a complexification of this, but we'll take of the simplest one, and we will very often use it in this course and in other courses here. Imagine you have to compute an integral, and this integral can be interpreted as the expectation of some function of a random variable or a random x. Here can be a very complicated thing, not just a single one-dimensional random variable. It can be a complicated vector with large number of dimensions, for example. So that's the first step. Assume you can interpret your integral as this here, and that's very often the case for us. For example, when we will do tests, we'll need to compute probabilities of something that's very complicated to express. So that naturally comes in this form. And assume you can simulate x here. You can produce samples of x using, for example, the methods we've just seen here. Then one way to estimate beta is to do the following. We can interpret beta as the expectation of this quantity, and we can estimate an expectation by estimating the mean. So if I consider phi of x to be a distribution, beta is the mean of phi of x. So if I can produce capital R samples of phi of x, then I can take the mean as given here. So that is the Monte Carlo generic simulation algorithm. I generate capital R independent replicates XR of this thing here. This is system dependent, of course, how I do that. Then I do simply the average of what I've seen here, 1 over capital R, the sum of this. And that gives me an estimate of beta. Of course, an estimate alone is not sufficient. So with Monte Carlo simulation, what we'll always require to do is to compute a confidence interval. And here the confidence interval has to be the confidence interval for the mean, so the one that's more tricky and more complicated. For example, assume somebody asks you to compute this integral here. So it's an integral of 4 variables. And we can see that it has a simple interpretation. If I consider the variable x1, y1 to be a point, then the density is 1 between 0 and 1. So this point x1, y1 is uniform distributed in the unit square. The point x2, y2 also, and the joint here, PDF, is the product, which means they are independent. So this can be interpreted as the average distance that we have when we draw 2 points uniformly in the unit square. I draw a first point, I draw a second one, I measure the distance. The distance itself is a random variable, and beta is the expectation of this random variable. Which, and I assume also in this specific case, that can be computed. There's a very, very long formula that was found not so long ago. But assume you don't want to do analytical thing, you want just to have a numerical estimation. Which of the two proposed algorithms, A or B, is a correct implementation of the Monte Carlo method? I close in a second. The majority says both, which is not correct in this case, and it's not correct because of a little bug in this one here. Oops. Because of a little bug here, and this bug is this versus that, right? This is the confidence interval. Of course, if I do a Monte Carlo simulation, I have a random output. If I do it another time, I'll find a different number. So we need to quantify the confidence interval. And you recognize that the correct formula is here. Capital R is the number of samples I have. And here I have a prediction interval, not a confidence interval. So both are giving the same, except their confidence interval error bound is not correct here. So the correct answer is B here. So I did it here, and I computed various values of R. So I obtained this number here, and my confidence interval, as you can see, decreases here. As I mentioned, the true value is known. It's this here. And I see that I need 1 million samples to obtain the fourth digit right. But if I'm interested in only a coarse approximation, even a very short simulation will give the thing right here. So take-home message, I mean, look at this paper. You will see that the formula itself is very long. Here, doing this algorithm is very simple. So Monte Carlo simulation is a generic method that can compute very powerful things. Now I used, for the confidence interval, I used the confidence interval for the mean. Is it a good idea, really? What do you think? I close the poll in a few seconds. Well, we would like to be safer and use the median, but here it doesn't work. And the reason it doesn't work is that by nature, the thing we are computing, we're estimating, is a mean. So it's one of the rare cases where we must use the confidence interval for the mean. So here we have no choice. So we have no choice, but we still need to be careful. That means we need to make sure that our R is large enough. And we will see several practical examples, but in practice, this is typically not a problem because we control R. So I gave an example where here I can compute the confidence interval. Here I see my output, and I can very easily see whether the formulas I have are providing an interval that is likely to be correct. So since we are doing a simulation, typically we need R to be large. We need R to be very large. I mean, you don't do 20 simulation runs for this type of things. You do typically thousands or millions of runs to obtain one confidence interval. So this is a method that is very easy to use in terms of development, but requires, of course, to do a large number of simulations and to be able to correctly use the formula for confidence interval. Well, that's the end for today. We have seen simulation, which is perhaps a very important topic because of its practical aspect, but also, as we will see again and again when we talk of model fitting in a few hours, because it helps us reason about statistics in general. Voilà, that's all for today. Now, the job is, it's up to you now to do the exercises on simulations that are online. So, as usual, we stay online and we're at your disposal for questions. Enjoy and see you next week.